What if I told you a simple coil of wire could resist changes in electricity without using a battery, computer, or moving parts? This tiny component stores energy in a magnetic field and is one of the most important building blocks in motors, transformers, and power electronics. Today, we're going to be breaking down inductance and how it actually works. An ideal inductor is an energy storage circuit element like a capacitor, but represents the magnetic field effect. Inductance can be measured in Henries, which is the unit and is symbol H. The inductance can be calculated by taking the magnetic flux linkage divided by the current, which is equivalent to the magnetic flux divided by the current. From this formula, N is the number of turns of the coil. Alright, now let's introduce some images. So here we have two inductor diagrams. The image on the left illustrates a single inductive coil, or an inductor of N turns carrying a current I that is linked by its own flux. Now taking our attention to the right illustration, this is the general circuit symbol for an inductor. So you tend to see this in wire diagrams or circuits when kind of introducing inductors into a diagram. Okay, let's get into a few more important things such as formulas and particular laws. So starting with Faraday's law of induction, we can express voltage and current relationships in the form of these two equations shown here, where the voltage across an inductor is equal to the inductance, which is a constant and not a function of time multiplied by the rate of change of current. We can rearrange the voltage formula in terms of current, resulting in the reciprocal of the inductance being multiplied by the integral of the voltage with respect to time from negative infinity to a time t. L is assumed to be a constant and not a function of time. And taking our attention to the center equation, where we have the instantaneous power delivered to the inductor, is given by taking the inductance multiplied by the current flowing through it and the rate of what is currently changing for the current. Lastly, the energy stored in an inductor at some time t is found by taking the inductance multiplied by the current flowing through it squared divided by 2. Now let's try to understand how inductors will behave whether they're connected together in series or parallel. So taking our attention to the left illustration, we have inductors 1 and 2 connected together in series, and the equivalent inductance would be just the sum of inductor 1 and 2. Now taking our attention to the right illustration, where we have two inductors L1 and L2 connected together in parallel, to get the equivalent inductance, we would first take the reciprocal of inductor 1 and 2, sum those values together, and in order to obtain the equivalent inductance, we would take the reciprocal of that sum. When more than one loop of current is present, the flux produced by the current in one loop may link another loop, thereby inducing a current in that loop. Such currents are said to be mutually coupled, and there exists a mutual inductance between such loops. The mutual inductance can be two circuits, is defined as a flux linkage produced in one circuit by a current of 1 ampere in the other circuit. The self-inductance L sub 11 is given by taking the flux linkage of its inductor produced by its own current. Similarly, the self-inductance L sub 22 is given by taking the flux linkage of its inductors produced by its own current. The mutual inductance L sub 12 is given by taking the flux linkage of inductor 1 produced by the current in inductor 2. And the mutual inductance of L sub 21 is given by taking the linkage of inductor 2 produced by the current in inductor 1. Continuing our coverage on mutually coupled inductors, if the current of loop 1 flows in inductor 1 while the current in inductor 2 is 0, the equivalent fluxes are given in equations 1 and 2 shown below, which is paired with figure 1 on the top left. Now say N1 and N2 are the number of turns in inductor 1 and inductor 2 respectively. The part of the flux of inductor 1 that does not link any turns of inductor 2 is known as the equivalent leakage flux of inductor 1, and that is shown in equation 3, and there's an equivalent similar approach for equation 4. The coefficient of coupling is given the variable k, which equates to the square root of the product of k1 and k2. When k approach unity, the two inductors are said to be tightly coupled. And on the other hand, when k is much less than unity, they are said to be loosely coupled. Alright, if you made it to the end, give yourself a pat on the back for getting through this entire video. If you found this lesson helpful and learned something new about inductors, consider leaving this video a like and subscribe to the channel for more engineering content in the future, and we'll see you in the next lesson.